here's the last lesson of this unit. Finally, we are writing some polynomial functions. So not too much challenge here. Or is there? Let's see. We're going to be able to write polynomial functions using these things called finite differences. Finite is the exact opposite of infinite. Infinite means it keeps on going. Finite means it doesn't. And objective 2, being able to write a polynomial function from its graph, or maybe have some points there. So I have the points. What's the equation that goes with that function? Okay. So objective 1, being able to write a polynomial function using finite differences. So as you can see in the picture here, I got a triangle and I got a square and I got a pentagon. These things are called figurate numbers. Figurate numbers because they make a figure. They make a geometric figure. So the one on the far left there, those are some triangular numbers. Now they keep on going. 1, 3, 6, 10, 15, 21, so on. They're triangular numbers. What it means is that I couldn't make a geometric shape with equally spaced dots with those numbers to make a triangle. Triangular numbers. Okay, and then you have the square numbers. Maybe you're familiar with these things. 1, 4, 9, 16, 25, 40, 36, 49. Right? It's just 1 squared, 2 squared, 3 squared. You can make squares out of them. They're square numbers. And then you have the pentagonal numbers. And hey, let me zoom in on those pentagonal numbers just for a second. Oh, look at those. Pretty cool. Okay, so this is an example of being able to come up with a function using finite differences, as you'll see in just a little bit. So starting ourselves off, we're going to jump right in here, find the 200th term of the sequence that's in the table below. 200th term. Man, would you want to find all 199 terms that come before that? If you do, that's crazy. So, you know, part of what we do in math is all about finding a shorter way to do something, finding shortcuts. And that's what a function will do for us. Instead of having, if we want to find the 200th term, we don't have to find 199 terms before that. We can find an equation and plug 200 into that equation and get our answer. A lot less work. So that's what this next slide is saying, is to solve this problem, you'd want to find a pattern there in the f of x, or the y values there. You want to see what the difference is between those terms. So let's go back for a second. Go back right here. Let's see, what is that pattern? I'll call it this pen. So from 3 to 7, I'm going up plus 4. From 7 to 11, plus 4. Plus 4. Plus 4. So, for example, I would expect the next one to also go up by plus 4. 19 plus 4, I believe, is 23. But do I, again, want to keep going and keep going? The answer is no. It's increasing by 4 each time. We're going to see that what that means is that's a linear function. And this 4 here is the same thing as the slope. It's the same thing as the slope. So, it could be, maybe it's just 4 times 200. Maybe that's what the answer is. Well, let's step back for just a second. What about the first one? Is that just 1 times 4? No, 1 times 4 is 4, but I got a 3. 2 times 4, that would be 8, but I got a 7. A 3 times 4, that'd be 12, but I have 11. Looks like all I'm doing is subtracting 1. So it looks like that I could get this answer by just going 200 times 4 and then subtract 1. Well, that's 800 minus 1, 799. And I didn't have to find all of the ones that came right before it. Okay. So when the x values are equally spaced, what that means is they're all going up by the same number. Look at our x values. It's going up by 1s. So these things are equally spaced. Then the difference between the y values, or the f of x values, are called finite differences. I'm seeing what they increase by. Now, in the previous example, the one that we were just working on, that number was constant. It may not always be that way, but for this one, it was constant. So take a look at this one. I can see in this sequence of numbers I have 1, 4, 9, 16. You may already recognize those numbers right there. So if I look at the differences between those terms, called the finite differences, 4 minus 1 gives me 3, then I'm going up by 5, then I'm going up by 7. Those aren't the same. Those are called the first order differences. And then sometimes what we do is we find the second order differences. We find the differences between the differences. Whoops. Okay, so here's another set of numbers. Okay, completely different set of numbers. 1, 3, 6, 10, 15, 21. Maybe those look familiar from that very first slide back there. And I find the first order differences. I find the differences between my y values there. And I'm going up by 2, then by 3, then by 4, then by 5, then by 6 and 7. Okay, then I find the differences between those, and those are called the second order differences. Going up by 1, going up by 1, going up by 1 each time. If that was not the same, I would find the third order differences. I'd keep going until I found a constant difference. I think this one is constant. Now let me relate this to something in physics. Okay, so in physics, what these y values could be, just lost my pen, where'd it go? Okay. So what the first y values, the ones in blue, that would be like the position of something. Maybe it's a position of a rocket that you launch. So this is position. Okay, and then if I find the differences between all the positions, what I'm finding there is velocity. Wow, arrow disappeared. Okay, now if I see what the differences between all the velocity is, that is the rate at which the velocity is changing, which is acceleration. Oh my gosh, is that a hard word to spell or what? I'm going to abbreviate that as ACC, acceleration, how fast your speed is going. So just kind of an application of something from physics. Okay, so as I said, usually when we find the finite differences, we keep going and we keep going and we keep going until we reach a constant value. You'll see why in just a minute. So on this example, it went all the way down to the third order differences, and that means something. That means something. So in order to figure out what that means, you're going to do a small little investigation here using these three functions. What I want you to do is pause the video and fill out this table, 1, 2, 3, 4, 5, 6, those are your x values, and plug in all of the f of x, all the y values for each of the functions. Make one of these tables for each one of the functions, and then find the finite differences. You should make a basically this is the question that you're trying to answer. Whoops, here let me scroll forward. What's the relationship between the degree of each function and its highest order finite differences? So let me go back here. You pause and find that for each one of those. See what you came up with. Alright, here's the first one, f of x equals 2x plus 5. I filled out the table, and then I found my finite differences. I found out what my y values were increasing by. They could decrease. You might see that in a bit. These were going up by 2 each, and that was constant. The first order finite differences were constant, and I'm going to call your attention to the degree here. Since this is a 1, the degree, which I'll call n, is equal to 1. All right? So if I look at the second function, the quadratic one that you were using, filling in the table functions there, in red you have the first order finite differences going up by 1, by 3, by 5, by 7. It's going up by odd numbers. Okay, those weren't constant, so you keep going. Each one of the red differences are going up by 2 each. So each time I increase by 2 more each time. That's what that's basically saying. So on the second order differences were constant. And I'll call your attention again to the degree. My degree n is equal to 2. One more. A cubic. So I found my function values by just plugging in each one of those in for x. And then in red, here's the first order finite differences. They're not the same. Keep going. I find my second order finite differences. They weren't the same. Keep going. I found in green my third order third order finite differences, and they were the same, going up by 6 each time. the third order finite differences were constant, and calling your attention to the degree, n is equal to 3. So the answer to this question then, what's the relationship between the degree of each of these functions and its highest order finite differences? And it's pretty simple. If your degree is n, if degree equals n, that means your nth finite differences, your nth order finite differences are constant. Nth order finite differences are constant. So just scrolling back through this, it was a cubic. Degree is 3. Whenever I find my function values, the third order are always going to be the same. If it was quadratic, my second order is going to be the same. And then finally, if it was linear, first order is the same. So the first one indicates linear, the second one indicates quadratic, and the third one is a cubic. If it was fourth order, then the third order would be increasing, and you would have to find what those were increasing by. All right? So then, in general, if a polynomial has degree n, then the nth order finite differences have to be constant. Now, of course, this assumes that your x values are equally spaced. The first one's 1, and then 2, and then 3, and so on. In red there, that's the converse of this. This goes both ways. Remember that from geometry? If then becomes then if. So if the nth order of your nth order finite differences are constant, then that must be an nth degree polynomial. And that's how we would come up with a function for it. I find the finite differences, find out what the order is or what the degree is supposed to be. So we can use finite differences to determine the degree. But, well, I was looking through my comic books the other day, and I came across this classic scene from a Star Wars comic strip in which Luke is asking Yoda, but how do we write that polynomial function? I know what degree it is. Maybe it's the third degree. And, of course, that's when Yoda answers, a matrix you will use. It's my best Yoda voice. Whatever. Okay, so that's what we're going to pick up in the next video. We're actually going to use a matrix, come up with one of these functions after we found out what the finite differences are. So stay tuned.